Hello guys, I'm Marcus. I'm here to talk about Fileless malware. Let's make a brief tour about why it matters and how we propose to solve this problem. So first of all, Fileless malwares are in the news. And the reason is that they are very different and very distinct from the traditional malware. Traditional malware usually operate based on files that are dropped in the file system, and when processes are created, they are created based on these files. And then traditional antivirus operate in scanning using distinct methods these files. So whenever a file is written on the file system, is scanned, or whenever a process is created based on the file stored in the file system, this process image based on the file is created. The problem is now malware is fileless. So it does not persist on disk. It does not have a disk counterpart. It operates solely from memory. And thus it's very challenging to be detected by the AVs that do not have a precise trigger to inspect files. Fileless malware operating, for instance, by tricking you into visiting a malicious website and then a malicious JavaScript. You write a malicious payload on the memory of a so far benign process and then take its actions from there. So the only way to detect this kind of malware is to scanning the process memory, because there will be no file. And well, to detect this type of files, AVs would be required to move their detection methods from file-based to memory-based. But here there's a problem. The problem is that the overhead of performing memory checks is very large. As you can see here, for distinct applications of the spec benchmarks, the applications, the overhead imposed by a AV scanning the memory along with the execution of applications might impose overhead of up 100%. And this happens because the AV and the applications must compete for resource. As you know, there is a shared bus, a shared memory bus between the processor and the DRAM. So they are competing to retrieve files, retrieve data from DRAM to operate or to scan. Of course, each application is affected distinctly because each one is distinct in characteristics of the memory access patterns. Some consume more data than others. But in the worst case, there's 100% overhead because the AV is always competing with the original application running. So what happens in practice is that despite somehow capable of scanning memory, most AVs and any secured solution disable memory scans, as you can see here for an example solution, but that could be multiple solutions. So memory scans is still not practical to be performed in real time and continuously performed. Thus, we need to find some way to improve the AVs to make this kind of detection practical and thus to be able to detect fileless malware. Current AVs are software solutions. So when you think about how to improve the AVs, we think, oh, let's make a better implementation. So let's take a look if it's possible. Well, the upper line shows how current AVs are implemented, current memory scanners. They are implemented in userland, so they have to perform lots of boundary controls, lots of translation, access tokens, and so on, so they are usually very slow. The lower line shows how forensic solutions are implemented. They are implemented in kernel using the physical memory dump without constraints, without border controls. This is very good because you don't have to take the overhead of many of these controls, and it makes the analysis much faster. As you can see, there's again of an order of magnitude if you would be able to change antivirus from userland to kernel land. But as you can note, the overhead is still non-negligible. And even worse, it grows linearly with the size of the memory. And for the future, we want to have each time more memory. So each time the overhead will be greater. So change the implementation. It's a small solution, a small step towards improving AV, but it's not the definitive solution. We need to find something more fine-grained, right? And well, to identify which resource or how could we perform this more fine-grained check, we need to understand what's the malware detection process. So we think what happens when you are detecting a malware? We are performing, in fact, two tasks, a monitoring task and a classification step. The monitoring is to continuously assess some resource, a file, a process, or whatever, to identify a given period of time that we need to inspect. We need a precise trigger to launch a detection procedure at that time. And after that, we launch a classification, a classifying analysis process that, based on resource that was pointed by the trigger, we classify it as benign or malicious. So we need to find ways to improve these two processes. First of all, we need to improve the monitoring process. So we'd like to have a trigger, something that say, okay, now it's time to inspect this resource. In our case, a memory resource. And we think about current architectures, what we have in the computer that's memory related. It's the page flow subsystem. So if you would be able to, each time that a page flow occurs, to scan only that floating page, you would be able to mitigate the overhead by not being required to scan the whole memory, by only the floating pages that are the pages that are going to be executed or read or so on. So as you can see here, an hypothetical example based on the same benchmark applications, you see that despite the number of giga cycles that are used by the applications, the number of page faults are smaller. So the times, the opportunity that you have to check are much lower. So this decreases the overhead because only in these opportunities you would perform a check. However, we still have a problem because we need to run the analysis process, the classification step. So each time that we have a page fault, we would be required to block for a given period of time so the AV can scan that page, the AV can inspect that page. We need to block because we should not need the malware to proceed its execution. So we cannot hide the overhead of performing this step. So I show you here in the table hypothetical examples of how much overhead would be imposed by blocking by distinct number of cycles. As you can imagine, the more complex the detection routine that is implemented by the AV, whatever it is, the more overhead is imposed, up to 20, almost 30%. Of course, when we started with, we are talking about 100%, and now we're talking about 30%. It's an improvement, but still not the definitive solution. We still do not completely mitigate the solution. So we need to move to something even more fine-grained. So what we proposed? Well, the malware is moving to the memory. So the detection techniques should move there too. The recent advances in in-memory and near-memory process show us that there's a lot of possibilities to integrate solutions that process data in memory so we can avoid the overhead of moving data to the CPU. So let's take a look on how the memory works and see if we can put something more precise here and more effective here to detect malware. So as you can see here, in the right we have the processor backend, in the left we have the DRAM, and in between it's connected by a memory controller. And each memory controller has at least two queues, a write queue and a read queue. Okay, so the first thing that we realize is that the write queue is the most fine-grained possible detection trigger that we have, because since we are trying to detect fileless malware, at some point the code will be injected in memory, so it will be stored in memory, so it will trigger a write in that memory. So at some point, this malicious data will fill this write queue, right? So if we use that as a trigger, whenever a write occurs in the memory from the processor to the DRAM, we can launch an inspection routine. So we can use that as a trigger. That's very interesting, that we are looking for. But more interesting than that, we have distinct policies that are implemented in this queue. So since we have a read queue and a write queue, most controllers allow some policy that's like read requests might overlap and might bypass write requests. So it allows the CPU have a very high throughput consuming data. There is only one case where you have to stop and perform the write request first. That's called read after write condition. But this case is very rare. In most cases, it does not occur, or it occurs after a long time. So after a write request is performed, the data is stored on the DRAM. Only a very large, or at least very significant period of time, this data will be further read again. So we have this opportunity, this window, this read to write window, or write to read window, to perform the classification step. So we have the best of the two worlds. We have a fine-grained mechanism to trigger the antivirus scanning, that is the write request, and we have a very opportunity to mask the overhead of the scan, putting it to happen between a write request and a read request of the same data. So this is our idea on how to mitigate the overhead of a memory scan. So in our model, we would still have an antivirus in software, but this antivirus would not be performing these tasks anymore. It would be only receiving the information of the data that's processed within the RAM without further overhead. So in a better way, I explained that at a very high level, since the details can be found in the paper. We have here our proposal for the mini-me architecture. That's the in-memory and near-memory evaluation of fileless malware. So it can be near memory or in memory because it's placed on the memory controller. So whatever the memory controller is placed, our mechanism is placed too. So let's imagine that this system operates on a network on a chip way. So we have here at one, a network incoming package. That is basically a write request. When it happens, as it's shown by the number 2, the data is usually written at the memory, at the RAM, as usual, as the memory controller often does. But in addition to that, in parallel, as shown by 3, this data is also scanned by our mechanism inside the memory controller. That's the matching engine. By this time, you don't need to understand what this does. It can be a black box. Whatever it does, it scans, as an antivirus defines, this memory. And after the scan, it's stored on a malicious bit database that stores the result of the verification for that memory position. And in the further moment, when the memory controller receives a read request package, it proceeds, of course, delivering the data as shown 5. But in addition to data, when assembling the package, it also reads the malicious database and assembles a package that also delivers a malicious bit, indicating that after a scan, this memory content is free of malware or it's suspicious, right? Of course, along with this process, we also have a whitelist because sometimes the detection might fail due to false positives, so we need to find a way to deliver more correct information. But what we want to show here, to showcase here, is that it's possible to launch a scan in parallel with the data to be stored and to be read from the RAM, and we can use that to inspect that memory content for malware, right? And then we deliver an already scanned page. And how to deliver this information back to the OS and to the antivirus and to the application. To deliver the information of the scan back to the OS, we rely on the previously presented pageflow mechanism. So we modified the pageflow handler, as you can see here for the Linux pageflow handler, to add more reasons for a faulting page. So now, in addition to the write flow or to a read flow, we have a security flow. So whenever a page that is translated containing the security bit set by the mini-me mechanism, it raises a security fault. This fault can be delivered to the antivirus that will now act as a policy decision taker. So in this case, it will decide that if this application will keep running, if it will be blocked, if that memory region will be whitelisted, or any other policy. But it will be delivered only for the faulting pages. It will not be applied to the whole memory or to all pages, only the ones that are about to be executed or about to be read, since you are interested in detecting malware that's actually executing. And okay, so far we have presented the overall idea of our proposal, that's move the AV detection mechanism to the memory. But now we have to present some concrete examples. We need to make this practical. And the first evaluation that we need to make this practical is decide what to put on that black box that performs the scanning mechanism. What happens in practice is that the more complex the detection mechanism that we put there, the more overhead we'll have. For instance here, repeating the experiments for the spec benchmark applications, now talking about the overhead on IPC, instructions per cycle, we notice that the more cycles that we block the memory to perform to take a decision to perform a scan, the greater the overhead on the IPC. Of course, for 0, no overhead is imposed. Up to 32 cycles per memory write, we have less than 1% overhead for all cases, and then we keep adding. So, although our proposal is generic, we could put whatever there, like a machine learning mechanism, it's very unlikely that it would succeed in making it practical because it would take many cycles. So you cannot perform this kind of complex check without the help of an accelerator or an external coprocessor or whatever. So we decided to operate in the simplest cases. So we set as target to operate in this region here from 0 to 32 cycles. So we would impose less than 1% overhead. So what would be the simplest matching mechanism that we could put there to detect fileless malware without causing significant overhead? And our solution is to use signatures. That you are basically a simple pattern matching. You are trying to match a set of bytes that are being written to the memory against a set of bytes known to belong to malware samples. Because in the last instance, we are trying to use this as a proxy for a high-level behavior. So in the case here, in the first code, we can see a high-level code construction that can be malicious. So at some moment, it will be translated in assembly and then in this set of bytes by the compiler. So if you are detecting this kind of bytes, we are in the last instance detecting that upper level, high level behavior. It's still very popular among antivirus. Signatures are especially used in the case of fileless malware because they are a fast way to react to a known malware. And previous fileless attacks have been detected due to that. For instance, there was a famous case in what signatures were used to detect the Metasploit framework inside the memory of benign process by its signature. So we adopted this approach since it's the simplest way to detect a malware. So you match the byte being written in the memory against a database of known malware patterns, right? But there's a lot of trade-offs to be overcome and a lot of decisions to be taken to allow you to perform an effective and efficient pattern matching, signature matching. For instance, the size of signature is very important because if you are using very short signatures, you have lots of false positives because you match basically everything. So each time there's a page fault, you'll be raising a notification to the antivirus to take further actions for that page because page fault. So you are not mitigating overhead in that case. But on the other hand, if you take a very large signature, you don't have false positives, but you have a very large storage overhead to store all that bytes for all that patterns because you are using a very large signature, right? In addition to that, we need to decide how to store such amount of information because if we use the table, for instance, with one entry per signature that we want to match, we basically have a linear growth of this number of the signatures. So you will have half of your memory populated with signatures instead of actual data. So it would not be practical. So you need to find alternatives. One alternative is, for instance, to use Bloom filter. That's a probabilistic matching data structure. So if you are able to correctly calibrate the Bloom filter, maybe you are able to present a very acceptable trade-off between the number of false positives and the storage overhead imposed to store the signatures in the Bloom filter. And finally, we need to define some scan policies because in the last instance, we could always scan the whole memory. Everything that's written in the memory could be scanned. But since here we are aiming to detect fileless malware, so in the last instance, they are instructions to be executed, we can rely on the fact that the page fault handler has access to the MMU flags. So we can identify if a page is only storing data or storing code, if it has the execution permission. And we can then raise notifications, for instance, only for code, only for pages that have the execution bit set and ignore the rest. So it would reduce the overhead of raising notifications. It would also reduce the number of false positives because false positives occurring in data pages would not raise detection notifications. So we need to decide how to configure the signatures regarding all these aspects. And what we decided in the end is to use medium-sized signatures, so 32 bits per signature, stored using Bloom filters and matching against only code, right? So this trade-off was the most effective according to our evaluation. And it's interesting to notice that the Bloom filter is a very nice choice because we could map 1,000 signatures of 32 bits each one in only 4 kilobits of data. Of course, there's not a register of 4 kilobit size to match. So what we do is to perform partial matches. So we take the largest register available in the platform and then perform partial matches of each time the size of the register until we match the whole signature. So far, the largest register that we have in a platform is the AVX2 register that is implemented by Intel for vectorial operations. So we have 512 bits to be matched each time. So if we keep performing this number of bits of pattern matching each cycle, we have to match 4 kilobits of data of a whole Bloom filter 32 cycles, which allows us to match the whole signature database in imposing less than 1% of overhead, as shown in the first graph, right? Of course, there's a lot of other trade-offs you should take care about. For instance, the number of registers. We chose to tackle the worst case, so we have a single register on the platform. But if you have, for instance, 2 of these registers, you could match the same amount of data in half of the time. So let's make things practical. So we implemented this evaluation that's basically to check the best solution that we could implement in software against our solution in hardware. So our software implementation is not a real AV, but it's an academic, lightweight solution for memory inspection that inspects only some memory regions that we re-implemented using the insights that we gained while inspecting how to speed up antivirus. So it's a very fast solution. And as you can see, it has significantly gains because in the beginning, you're talking about 100% overhead, and now you're talking about 13% overhead. And now you're talking about execution time. So the number of seconds that we spent to scan the memory along with executions of one of these benchmarks. But even faced to this very fast application, our hardware solution was still outperforming this solution. So in no case, regardless of the application that was considered, we imposed no more than 1% overhead in the execution time. So this shows that we can basically fully mitigate the overhead of memory scans by moving our solution too close to the data. So put the antivirus matching engine inside the memory where the data, the malicious data, is stored. So our conclusions, our closing remarks is to show you that fileless malware are challenging to be detected and they are likely to grow in the future. So we need since now to pay attention to that and try to identify new ways to detect that, like using hardware, because software-based solutions, you always have the overhead of competing for resources. And then we presented Minimi, that's our solution for hardware-assisted pattern matching targeting fileless malware. So we would move parts of the antivirus engine close to the memory. Ideally, it's a platform for further developments because it could be a black box matching mechanism. It could be anything. But for the concrete case here, we used signatures, which does not mean that our development is finished. It means that it's the first step and other detection mechanisms should be investigated by the community to be moved to the hardware as well. And we believe that this could be a first step and hope that other researchers will also investigate other possibilities. Finally, there's also some code available. I'm available for answering questions, for hearing your opinions, your comments. You can reach me by email or on Twitter. And thanks for your patience, for your time. Thanks for having me. Bye-bye.